tree on our left side when we came over here. Can anybody tell me what kind of really big tree that is?
Redwood?
It's a Douglas fir, but they often get mistaken for redwoods. So that's that really red colored bark you're seeing, and then those really deep grooves as you look up higher. So in our forest, if you see a tree and you think it's a redwood, it's probably a Douglas fir. So they're really impressive. They're gonna get really big and fat, much like our Sitka spruce trees. But as we were walking by that tree, you may also have noticed that there is a branch sticking off of this tree, about a quarter of the way up. And most of our trees do not have branches down that low. So I can tell you that that is not actually a branch. What happened is that at some point, that tree got a little injury. Maybe it did have a branch there and it fell off, or another tree caught the side of it when it was falling over, and it kind of scarred over the same way we would when we get an injury. And over time, that scar collected debris that fell from the canopy, and eventually it caught a little western hemlock seed. So now, there's a western hemlock growing up the side of that Douglas fir, which is pretty impressive. And if you are able to see it well enough, there is a root reaching from that western hemlock all the way down and into the ground. So that tree is not growing into the side of the Douglas fir. It focused all of its energy on getting that root all the way down and into the ground. So they're not hurting each other. They're just going to grow together for as long as they can. There's a good possibility that western hemlock will get too heavy and kind of fall off the side. But I love looking at this Douglas fir because it shows us some really amazing things. Not just how amazing Douglas fir trees are, but also that all of their needles are way up high. That's where all of their branches are. That's because way down here, there is not as much sunlight. So these trees have focused on growing their branches way up high where they are able to get all of that sunlight and do all that fun photosynthesis, get all those sugars that they need to survive. And they're going to let those lower branches that are not getting sunlight stop producing needles and just kind of fall off. So that's why all of our trees have those needles way up high. I stole this analogy from one of my other ranger friends, and I do so shamelessly. You can think of it like you are going to put solar panels on your roof. You are not going to put solar panels in your basement. That's the same thing our trees are doing. So all of their needles way up high. But all of our trees here also are not digging down deep with their roots. They don't have those deep tap roots because this soil is really rocky. It's hard to dig into. That takes a lot of energy. It's much easier to just spread out as far as they can. And all the nutrients that they need are right up at the top anyways. So why dig down deep when they don't have to? So they're just kind of stretching out as far as they can. They have really wide, shallow roots. So that means all of the weight of our trees way up at the top. They're not really holding on very well. So say a big gust of wind comes through and now they are really big and tall and getting really, really old. Eventually, they're going to fall over, which is okay. That's what our big trees want to do. That is their retirement plan. That means they lived a nice long life. They are eventually going to fall over. That's okay. So someday this Douglas fir tree will fall over. There's a good chance that western hemlock could still be growing on the side of it when that happens. It might just keep on growing. It might go down with that Douglas fir. Who knows? But our big trees are going to fall over. Those roots are sitting right up at the surface. Because all of these roots are sitting right up at the surface, that means that some of these really important parts of our trees are also sitting right up at the surface. So our tree roots have this thing called root hairs. Very original name, very descriptive. So when I pass these pictures around and you're looking at these pictures of roots, you're not just looking at this kind of line of white, you're looking at all the tiny little hairs sticking off of those roots. Those are the actual root hairs. So I will pass these pictures around. And when you're looking at these pictures, you want to think about where these root hairs might be growing because they are going to cover the entire root.
That's fine, yeah.
So these root hairs are what absorb all the nutrients that these trees need to survive. They're sucking up all that water, all those tasty nutrients in the soil so that they can get used by the tree and sucked all the way to the top of those trees. So they're really important. They're a vital part of these trees. But the thing about root hairs is that they are really fragile. And one of the ways that they can get broken is by us going off trail. So if we step on enough root hairs, we can kill trees that that are really, really big. So our small boot prints, or at least my small boot prints, have really big impacts. We were seeing this happen to even the big sequoia trees down in Sequoia National Park. People were trying to give those trees too many hugs. It was crushing those root hairs and killing the trees. So that's why a lot of those trees are surrounded by boardwalks now. Out here, we can't really have as many boardwalks because wood is gonna rot pretty easily here. But we are lucky enough that these trees know this soil here is really compacted. It's really hard. They're not gonna be growing new root hairs under here. So as long as we are staying on trail, we're good to go. We're not stepping on our tree friends' toes. So we're really nice to our trees here. But we also know that because this forest is so old and so well developed, there are some other ways that it might be able to get the nutrients that it needs to grow. Exactly how this happens, we don't know for sure. So there's a few theories, and one of those theories is that we have something that is known as a mycorrhizal network, which is a really fancy term for kind of a mushroom network. So what's happening is that you take a tree root and you connect it with a mushroom root, theoretically. It's kind of the easiest way to think of them. They are going to connect. And then that mushroom is going to take that tree communications, connect it to another tree, and now those two trees can communicate. They cannot talk to each other like you and I. They cannot say words, of course, but they can share chemicals, we think. Again, this is all new science. It's all still a theory. We're not exactly sure what's going on. But one theory is that we think we have what is known as mother trees. So these really, really big trees that have been here for a really long time have those needles way up at the top. They're probably getting more nutrients than they need. So they could share those excess nutrients, thank you, with all of these baby trees down here that are not getting all of that sunlight. So we think they're able to share that. And that's what they're using that mycorrhizal network for. It's kind of the sharing of chemicals, the sharing of nutrients. We also know that these trees are not communicating just Sitka spruce to Sitka spruce or Douglas fir to Douglas fir. They're talking in between species. So the Douglas fir can be talking to the Sitka spruce could be talking to that red alder all the way down by that water down there. So the trees are able to connect this whole forest. We like to call it the wood wide web, or the social network of trees, but it's allowing our forest to work together. It's a little bit more collaborative than we originally thought, but like I said, this is still really new science. We're still figuring out how this all works. There's also a chance that it's just the tree roots hooking up with the other tree roots, and the mushrooms are just kind of there anyways. So they may not even be part of the network. We don't know. We're still learning, and that's what makes having these old growth forests so important, so that we can come in here and still learn new things about our world, which blows my mind that we haven't figured it all out yet. But if you ever want to fall down another rabbit hole, look up the mycorrhizal network. It's really crazy stuff. It takes way more than 90 minutes to explain, so I don't have time. But I know I threw it at you very fast. So if you have any questions or want me to clarify something, please feel free to ask.
How do they study that?
Yeah, there was a scientist who, well, she was a forester. She was logging, and she saw one tree, really, really big tree. Then she saw a mushroom, and then she saw a little baby tree. And she was by the big tree, and she pulled on a root, and the mushroom moved. Mm-hmm. And then she went by the mushroom, and she pulled on a root there, and the little baby tree moved. So what she did is she inserted like a radioactive substance that she could track and see where it went in the forest. It wasn't harmful, but it was just something that she could use to find where that substance is going. And it went from the big tree to the mushroom to the baby tree. So that's kind of how we discovered this possible mycorrhizal network. That study is one of the older studies that is in this subject, and now some of it has been disproven. So we don't know for sure how exactly it's working, but that's kind of what introduced us to this idea that our forest is a lot more collaborative than we originally thought. Yeah, good question. Any other questions? If not, we're gonna go around the corner and meet our final conifer friends.